Hi, thanks for joining in this talk about developing Java applications leveraging the quantum internet in 15 minutes. It's quite a challenge to do this in 15 minutes. It's actually a challenge to do this in 15 hours. It's actually a challenge to do this at all. So let's get started. I'm Johan Vos. I work with Gluon, a company that enables Java as a first-class citizen on mobile and embedded enterprise. And the background of this talk is I'm writing a book about Java, quantum computing for Java developers. Manning, being a media sponsor of Devox, is offering a 40% discount for all the Manning books with that code. And I can give 5 ebooks away. If you tweet with the hashtag QuantumJava, I had to think very hard about the system. So if you tweet with that hashtag, I will tonight or so look at who tweeted it and then do a raffle, and I will send direct messages to the ones who get a code that gives a free ebook. So I'm talking today about quantum networks and not really about quantum computers. And those things are different. So very briefly, what's the difference? A quantum computer is mostly known for it's more popular in the media because it's supposed to break encryption. It can help with optimization problems, with medical research, with understanding nature. But it's hard to create. It requires a large number of qubits. We will come back to that later. And the real hardware that will allow to do this, that really ready for production, is many years out. Some say 5, some say 10, some say 15, some say never. But there exist simulators. For example, Strange is a Java-based quantum simulator. So that's a quantum computer. What is then a quantum network? A quantum network connects quantum computers, allowing to send qubits from one computer to another. And it allows to do secure communication, which is also the basis for many applications. And it can be created using optical fiber, so the what is already typically used in today's internets. But it also requires more than just that. It requires also quantum repeaters, as we will explain immediately. So first of all, who here does know the concept of a qubit? Okay, that's almost 50%, I think. So very briefly, a qubit is the most granular entity in quantum computing, and that can hold a value of 0, like a bit, the value of 1, or it can hold a combination of 0 and 1. At the same time. I know that some physicists don't like to use the at the same time, but it makes it easier to understand, I believe. Note that I draw arrows, so the value 0 is pointing downwards, value 1 is pointing upwards. This corresponds, for example, with the spin of an electron, which is one of the physical ways to implement qubits. I'm not going into any details on how we do this on a physical point. Just assume that this is mind-boggling, crazy work, and some clever people are doing it. Another concept in quantum computing is superposition, and you might have heard about it as well. So very briefly, when I said that a qubit can hold the values 0 and 1 at the same time, it actually means that it can hold 2 values. So with 2 qubits, we can hold 4 values simultaneously. With 2 bits, you can have only 1 value simultaneously because it's either 0, 0, 0, 1, 1, 0, 1, 1. But with qubits, because they can hold 2 values at the same moment, each qubit, this counts exponentially. And with 100 qubits, we can hold 10 to the power 30 values simultaneously. And that's a large number. And that is what gives quantum computing, what makes it so promising, that we can tackle exponentially scaling problems. The other concept that's very important in quantum computing is entanglement. And with entanglement, we can create 2 qubits that still have values that are a combination of 0 and 1. But the thing is, once you measure one of those qubits, it will always give a value 0 or 1. And the other qubit will give exactly the same value. So those 2 qubits, even if you send one to the other part of the universe, the moment that you read one, the other one will have the same value. It's like you're tossing 2 coins, and while they're up in the air, you take one and you go to the other part of the world. The moment that you see this is heads, the other one will have heads as well. So that's very difficult, if not impossible, to understand with our brains. But it's an important aspect of quantum computing that has many great applications. Nocloning theorem is important as well for us because it actually means that a qubit cannot be copied. And that makes it tricky because if we are doing networking, we typically copy bits, but qubits cannot be copied. That makes it difficult, but also secure. So there are a number of challenges when we want to create quantum networks or quantum computer. The fact that we can hold a huge number is very promising, but on the other hand, once we measure a quantum system, all those qubits will fall back to a value of either 0 or 1, not a combination anymore. So people then ask, yeah, what's the benefit if I can do hocus pocus with many values, but in the end I get one value again? The trick is that you have to transform your software problem into a problem that's applicable to quantum computers that takes advantage of the exponential scaling. You do some gate processing, and then you transform your problem back to the original space, and you measure it, and hopefully the value that you measure then tells you something about the problem that you want to achieve, that you want to investigate. For example, if you do integer factorizations, you use this to detect the periodicity of a function. And that is then related to how can integers be factored. So that is software development. That is, it's pure software development, but it leverages the exponential scale-up of a quantum processor. Applications, the typical ones are encryption, but also molecular biology, healthcare, and optimization problems. Those are areas where we think that quantum computers can make a big difference. As I said, this requires many qubits in order to be production ready. And that's not ready for tomorrow. So, well, when we say 10 years, it's the day after tomorrow. If you look at the age of the universe, that's the day after tomorrow. But what is possible tomorrow? And that's why I want to talk about the quantum networking. There is, for example, there are many projects that are leveraging quantum networking. One of the most interesting projects to me is what's being done in QTech, which is an organization that's linked to the Delft University of Technology. And there they are working on a real quantum network that will connect 4 different cities in the Netherlands. And their aim is to get this up and running in 2020. And that will then lay the foundations for a real quantum internet, because they will learn from it and they will send qubits from quantum computers between those different cities. So what is a quantum network doing? We're transferring qubits from one place to another, from one quantum computer to another quantum computer. That allows for secure communication, and that's actually the basis for many problem areas that are currently impossible to solve with existing computers. It's currently working for short distances. For short distances, you can use optic fiber, but for long distances, you need more clever hardware. So how does that work? If we connect 2 computers with a small quantum processor, and it can be shown that actually you only need a quantum computer with 1 qubit, that's already enough, and those exist. They can already take advantage of quantum networking. And they can communicate over telecom fiber, and that's fine. But what if you connect many computers together? Well, you would hope that you can connect them one-one, so that every computer is connected to the other one. That's not how traditional networks work. We work with switches in between. What's the difficulty here with quantum networks is that a switch takes a bit and directs it to the right direction. But it has to inspect the bit and see if it's 0 or 1 and then put it on the right place. But a quantum bit, a qubit, cannot be inspected because then you're destroying it, actually. That's the Nocloning theorem that I discussed before. So we have to transfer qubits and reroute them without looking at them. And that's that makes it much different from traditional switches and routers. Also, over long distances, repeaters are needed because the signal becomes noisy. You can talk about it for a very long time, but the quantum superposition state is very hard to maintain, and entanglement is hard to maintain. So the longer the cable, the more likely that it will be too noisy and your measurement will be broken. So we need repeaters. But again, we cannot just take the qubit, read it and amplify it and send it again. So that makes that makes it much harder. So that makes quantum devices, switches and repeaters much harder to create. On the other hand, once you have a system to create switches and repeaters, they are inherently secure because of that nature of quantum entanglement, which allows to create something that if someone tries to eavesdrops, you will notice it because the qubit that your other partner is going to send will be destroyed because someone read it already. I'm taking some shortcuts here to explain it in 40 minutes. So quantum circuits are actually similar to classical circuits where we have gates. We have the logical AND gate and OR gate in classical computing. We have gates in quantum computing as well. And the circuit that you see on the right is actually a very short description on how we can somehow teleport qubits. It's called, often called qubit teleportation, quantum teleportation, but it's not teleportation like you see in Star Trek or so. But it allows to send a qubit called size C there to B, and those can be on different places. And you do that by leveraging quantum effects like entanglement and superposition. In classical networks, we have the typical OSI model with different layers. The physical layer, which can be represented by different solutions. And then on top of that, we have the data link layer, network layer, and so on, until we arrive at the application layer. As a Java developer, you almost never deal with anything below the application layer. So the goal is to create something similar for the quantum networks, that you do not have to deal with the lowest layer, which is in this proposal, for example, the device layer. So this is from one of the talks of someone from QTech. What they're working on there is they're working on a standardization similar to the OSI standardization that standardize how higher level languages like Java can deal with lower level networks. And there's a Quantum Internet Alliance where this is also being discussed. And there's a simulator that's created by QTech. And they have a CQC protocol, which is at the top of this stack, and which is actually interesting because it can be used in Java. And strange, so the quantum simulator that I'm writing for Java, it allows you to work with quantum concepts in a very intuitive way with a Java API. And I'm having a pull request for implementing the CQC protocol there. So that means that then you can use Java code to write applications that leverage the quantum network. At this moment, that's a simulator, but once, hopefully in 2020, they show that it's really working, your applications should be possible to run on that real quantum network. And it will start in the Netherlands with 4 cities, but because it only requires a small number of qubits, it's easily to expand. And this is some Java code that is leveraging the strange simulator, and that is using the CQC protocol. They wrote it in Python with a C interface, and I added the Java interface. So this looks very much like Java NetSocket. And that is actually the goal. I want to have something similar like Socket, or maybe even Socket with some options that allow you to communicate between two endpoints using qubits instead of just regular bits. So that is extremely briefly. In summary, again, quantum computing is going to be very disruptive. It's hard to realize, but they're making amazing progress. Quantum networking is going to be there much sooner, and it will be based on the same aspects, but it will be ready for real-world applications much sooner. And you can start today by using simulators to write Java applications that are targeting quantum internet. And we hope and we're confident that real-world public networks are coming soon, so that your applications that you're developing now can work on that, especially if you're working in areas that require security. I think it's wise to look at this already. So that's I'm currently having 4 chapters of this book in early access. 5th is coming soon. Quantum networking is gonna be part of chapter 6. And yeah, that's the discount code. And tweet with Quantum Java, and you might get a free ebook. Any questions? You can grab me. I'm wearing a Quantum T-shirt or a DevOps hoodie. So, yes, one question there.
I was wondering, how do you handle the without transforming the qubits?
Yeah, the question is how do you handle the computation with the logical gates without destroying the qubit? That is the mind-boggling part that the hardware people are doing. They are cooling qubits till, in most applications, till 10 millikelvin or even lower. I keep forgetting the number. And there the qubits stay in the state. And then they, by using, for example, lasers, they can modify the behavior of the qubits. For example, they can switch the spin of a qubit, and that will change its value from 0 to 1. Or they can, with another technique, they can apply a Hadamard gate, and that will bring a qubit in a superposition. And that is working in this, you maybe saw this cylindrical computers from IBM and Google, for example, where the chip is really smaller than an inch, and then you have this huge cooling system. It's similar to the old computers in the 40s and 50s. Okay, time's up, but if there are more questions, feel free to ask them. Thank you.